Hi everyone, I'm Alexandre Blain, second year PhD student at therein in Paris, and today I will present Notip, which stands for Non-parametric True Discovery Proportion Control for Brain Imaging, which is originally a paper published with Bertrand Thirion and Pierre Neuvial in Neuroimage in 2022. So the problem that we are trying to tackle in this paper is the problem of brain mapping, which you're all familiar with, which is the idea of trying to map relevant brain regions to certain cognitive functions. So you have a few examples of contrast here on the slide. And so from a more concrete standpoint, we will do that from this type of input data, which is simply here 16 statistical maps and one per subject. That you have with a subject that is performing, each subject is performing a task. And so from a more technical standpoint, we can view this as a multiple testing problem in the sense that what we are trying to do is testing simultaneously each of the voxels in the brain, with the null hypothesis being that the voxel is inactive for the task that you're looking at, against the alternative that it is indeed active. And so you have a massively multiple testing problem since you have around 50,000 tests to perform simultaneously on this data. Okay. And so this is the first step that we perform when we are trying to tackle this problem, which is to perform, let's say, one sample t-test across all 16 subjects. And so there, from these 16 subjects, you obtain a single statistical map, which is equivalent to a vector p-values. And so generally, inference will be performed by some sort of thresholding on this statistical image, meaning that you want to retain relevant regions for the cognitive function that you're looking at. And so you will choose a sort of an arbitrary threshold to retain a form of relevant regions. So this is what you have on the slide here. Okay, so once you've done that, the question is, how can you perform inference in the sense of the operating on this region that you're extracting? And so something that is quite common actually in the community is to perform some sort of cluster level inference, so operating at a scale of clusters. So let's say that we retain the cluster on the right here, the red one. The idea of cluster level inference will be to look at the size of the cluster that we've extracted. So here, 877 voxels, and to compare this size to a certain null distribution that we have at our disposal. That is basically telling us what the largest cluster size should be under the global null hypothesis, meaning if there is no signal at all in the brain. And so then we will compare the size that we obtained to this size given by the null distribution and take a binary decision. So if our size exceeds the one of the null distribution, we will declare that the cluster in question is active. And so this is the idea of cluster level inference. Okay, so the problem with that is, if you really think about it in terms of statistical guarantees, you're really not getting much information out of this type of inference. In the sense that what you're really guaranteeing is that at least one voxel is truly active in your cluster with high probability. But of course, when you're dealing with clusters that have hundreds of voxels or even thousands of voxels in modern MRI images, you're really not saying much with regards to the extent of the signal within the cluster that you're looking at. And so another way of framing the question of brain mapping when looking at clusters would be to formulate a TDP, so the TDP, which is a true proportion of active voxels, a TDP lower bound in your cluster. So let's say that you would like to find that there are at least 50% of voxels that are active in your cluster. So this is what we are trying to do. And the big problem with this is that you're basically running into a selective inference problem, in the sense that you're using the same data for selection, meaning forming your cluster, as we've seen before, since you're thresholding the statistical maps, and also for inference, meaning to try to formulate a TDP lower bound. And so this can lead to, so this is what's called double dipping frequently, and this can lead to a huge amount of bias in the sense that might get a huge amount of false positives. And so I want to show you this very concretely on a very simple example in 2D. So here we generated some noise. So this is completely, I mean, this is Gaussian noise. There is no signal at all. And we've computed the p-values on this this 2D grid, this null data. So here you have a null p-values map again. So there is no signal there. And so the most common approach that people will use to reject some hypotheses there is to use Benjamini-Hochberg procedure, which is a most common solution to multiple testing problems. And okay, if we perform the Benjamini-Hochberg procedure on the whole 2D map, we get no rejections, meaning that the FDP, so the false discovery proportion of the set that we rejected, which is empty, is of course 0%. So this is exactly what we want, in the sense that there is nothing to find and we actually find nothing. But now, if before performing the Benjamini-Hochberg procedure, we perform a selection step, which consists in thresholding the image. So here we've retained the 10% of the image, which corresponds to the well, the 10% of smallest p-values. And now we perform Benjamini-Hochberg on this subset. We get 62% of the selected p-values that are rejected, which is absolutely enormous. And we get an FDP, of course, of 100%, because since there is no signal to find, every detection is a false positive. So it's normal that the FDP is 100%. So basically what this simple example shows you is that we are taking enormous risks on this subset because for absolutely no reason, because there is nothing to find, but simply because we have performed basically a data-driven selection step, which is this thresholding step, and without taking this into account. So this is typically a type of problems that can arise and that we'll try to tackle using Notip, and so the method that we'll now present. So basically a solution to this problem is to use what is called, is to basically control the number of false positives in data-driven subsets, so typically clusters. And so this actually goes way back in the literature, and this is what's called post-hoc bounds, which basically are valid bounds on the number of false positives in any data-driven subsets. And so first bound of the kind used in neuroimaging was the RE bound, which is published in Neuroimaging in 2018. So you have the expression on the slide, but no, it may look a bit complicated, but the only thing that you must retain from this expression is that here you have p-values, so py of x, and you're comparing them to a threshold family. So here alpha k over m, with alpha a certain level of risk, and m the number of voxels. So this is really the only thing that you must retain. We are formulating a bound based on comparing p-values to a threshold family. And so this is of course a valid bound actually, but so why is this not optimal? So why can't we stop there? It's actually that here, as you see, the threshold family, so alpha k over m, is completely parametric in the sense that alpha and m are well fixed beforehand, and so therefore this bound is not adaptive to data characteristics, in particular to the smoothness of the data. And so this leads to conservativeness actually on fMRI data. And so this is why we need to go further. And so first step that's been performed in the literature to go further is to use sort of semi-parametric bound, in the sense that here what you see is that the threshold family is still linear in k, so we have lambda k over m, but lambda will be chosen using randomization on fMRI data. And so this is what we call a sort of semi-parametric bound, because the bound is adaptive to data characteristics, but you are still keeping a linear function here in k, and therefore you are not fully non-parametric, because there's still a constraint on your threshold family. And now, so what I'm presenting to you today is Notip, which we have published in Neuroimaging in 2022, where we achieve a completely non-parametric bound, in the sense that instead of using a linear family, so lambda over M, with lambda to tune using randomization, we use a TK, which can be potentially non-linear, which can be of arbitrary shape, which is not restricted to a parametric family, and we learn TK from the data itself. So this is a completely non-parametric approach. And so what we want to show is that there is actually a lot of power to gain by using a fully non-parametric approach compared to parametric or semi-parametric approach. So this is what I want to show you now on real data. So to go back to things that are a bit more concrete. So here we've chosen a data set from NeuroVolt, and the type of inference that we are performing is that we are trying to find the largest possible region that satisfies that its force discovery proportion is at most, let's say, 10% here. And then we are looking at the size and the location of the region that we find with each method. So with the RE method, so again, that is parametric, we find a region of 2000 voxels approximately. While with Notip, so fully non-parametric approach, we find a region of over 6,000 voxels, which is a huge gain. So it's a region that's almost 3 times as big as the one we found the parametric method. So this is an example of a single data set. So we've performed extensive experiments in the paper, and I want to show you one of them. So to show you that we have not cherry-picked basically a single data set on which we saw some power benefits. We've performed this comparison on 36 real fMRI datasets we fetch from NeuroVolt. And so basically the comparison that you see on the slide is done in different settings. So we are looking for different FDP guarantees. But overall, you see that here in the second group box plot, so you are comparing Notip, which is fully non-parametric again, to RE, which is parametric. You have a gain in terms of region size of around 40% across basically all settings that we've considered. So each dot is a real fMRI dataset. So you see that these gains hold across many different real fMRI datasets. And so to conclude, so we've seen in this or presentation the relevance basically of multiple testing for brain imaging, especially the problem of brain mapping. Also the need for post-hoc bounds, so with RE and Notip, and especially the problems that can run into with false positives if we do not take into account the selective inference problem. With regards to the main contribution of Notip, we have seen that we can adopt a fully non-parametric approach by learning this threshold family TK and gain a lot of detection power, so around 40% compared to RE. And so to finish on one of perspective, so here we are what I've shown today is simply a one sample and two sample designs, and we can go potentially further, more general designs for instance, in the GLM, so the general linear models. Okay, there is a preprint by Sam Davenport on this topic. And I want to stress that everything that I've shown today is fully reproducible using the Python code of the Notip repository that is on the slide. And of course, you have details and many more technical stuff in our 2022 Norwich paper that you have linked on the slide here. So thanks for your attention, and goodbye.